I seem to enjoy the road. I seem to enjoy the road. It's, you know, the road's just kind of fun here.
Is it easier to find stuff here or in Enid?
Finding stuff?
Yeah.
Well, I don't know the buildings as well over in Enid, and I'm only in 2 buildings over there.
Are they in a circle like us?
They actually are the old Phillips University campus. And so they've got several other buildings and they've got a whole bunch of other stuff. So each
Excuse
campus
me,
is different.
Professor.
Yeah.
I think Veronica was asking if you were able to go over one of the homework problems. I don't know if you saw it in the chat.
Okay. Which homework problem are we talking about? And you can't just tell me problem number 3 because I don't know. $11, but you gotta tell me which what 11 is. You gotta ask me, you gotta fill in more information. Okay, it gave us the position of the block with the horizontal springs and expression of the magnitude of the block and the velocity. The maximum position is observed at the amplitude. Use the following. Assume the velocity is measured in meters per second. Do not include units in your answer. Okay, look at the solutions video. I think there's a solutions video out there on it. I am not going to make up numbers at this point, but I will probably send that to me in an email, and I will probably get it out and post it as a solutions video. Okay? And let's see if I can save the chat. Because that's the best thing for right now on those, because I haven't even had a chance to go in and look at which problems that you guys were having trouble with. I haven't had a chance to do that, but I want to get us through some more theory today so that we can actually be moving on. All right, so we talked on Monday. That we could have longitudinal and transverse waves. And we developed that position equation with the K and the K and the X and the omega and the T, and showed that a wave in a string is like a series of simple harmonic oscillators. But now we're going to jump into talking about sound. And you will notice that these slides were prepared for this old Searway book that I have. So this set of slides was prepared for the Searway book, and we've been working in the Katz book, but there's some things I like about this that I want to kind of cover a little bit more. So, sound travels as a longitudinal wave. Oh, we got to go back here. And we categorize sound as audible, what we can hear, infrasonic, those sounds that are at frequencies lower than we can hear, and ultrasonic, those sound frequencies that are above what we can hear. Think dog whistles. So dog whistles are ultrasonic, infrasonic are elephants, for example.
That's great.
Elephants actually have very low sound ranges. So that's how we classify sound, and audible is in our hearing range. We alluded to this on Monday. Making sure I got it recorded. Okay. We alluded this on Monday. So if I'm taking a speaker, which is one of the reasons why I gave you that interactive, so you can actually see the rise and fall based on the speaker. If I'm doing that rise and fall based on the speaker, and if I look at it as a piston, you see that I'm going to compress all the little air molecules and start pushing them. So the air right at the very beginning is going to be a little denser. And then as the piston pulls back, I'm going to get that rarefication. So the wave is going to go out as a pulse through the medium. Now, whether that medium is air, ether, water, wood, or steel is going to affect the speed. Like we showed before, remember we did that square root of the tension divided by the linear density? You're going to see this a little bit more. We're going to get that longitudinal part going through. And where we got to on Monday was I could write a wave equation. This one is in terms of S, but we wrote it in terms of Y. S maximum is going to relate back to the amplitude of the wave. How big is my wave? Or how small is it? It's also, you could think of it as displacement. So if I'm bouncing on the spring up and down, it's how far away from that equilibrium point am I at? Don't get that confused with peak to peak or valley to peak. That would actually be twice the amplitude. That is a common mistake. Okay, that's a common mistake. And K is what we call the wave number. Omega is our angular frequency, and it's the same angular frequency we were dealing with our simple harmonic oscillators. So in a gas, we can look at this as in terms of pressure. Okay, we can look at this as in terms of pressure, and we can look at that change in pressure. It also has a sinusoidal type behavior. We can also look at it and we can relate it back to this displacement, and instead of a linear density, we're going to have to play with the bulk modulus.
What does that mean?
The bulk modulus is related to the mass per unit volume and how stretchy it is. So linear density was mass per unit length in a rope, but if I'm dealing with air, I'm dealing with a volume, so I have to take it up a notch.
So is it like specific volume?
No, bulk density is going to be,
You said mass?
it's related to mass, but it's how it's going to behave. The bulk your bulk modulus, remember, it's also going to relate back to its restoring force. It's related back to its inertia associated with its restoring force. So I could have something that's brittle is going to have a different bulk modulus than, say, a solid rubber ball will. Okay? So if I have a solid rubber ball, it's going to be how much that something can deform and return back to its shape. It's that last section, that last part of the chapter when we did, when we started talking about solids and we started talking about stretch, and like a rubber band would stretch and then it would return back to its original shape. I could do it as a length. I could look at it from that. One's a Young's modulus. Bulk modulus looks at it in terms of a volume. Young's modulus looked at it just in terms of a two-dimensional structure. So think of shear. When we talked about shear, we looked at how something would shear. Bulk modulus refers to that from a volume. And so it's a property of the material more so than it is an overall density.
It's just based on like how much you can.
It's that deformation and restoring force. Bulk modulus is a material property. And so think for a second, all right? Forged in Fire, I love Forged in Fire. It's one of my favorite shows. And they're brutal. Everybody's watched Forged in Fire?
Yeah.
Yes, no? Okay. Now, think about this for a second. So you got Forged in Fire, and they do either the rattan mat slice or the bamboo slice, and you watch that bamboo thing will come back and go back up. And so part of what they're doing is they're dealing with the bulk modulus of the object to see whether or not the knife is actually going to slice through it. And they're dealing with whether or not the knife deforms. It's and you'll notice it is a function of temperature because you shouldn't be hitting a knife on a block of ice. Let's just be honest. And that's going to actually change your bulk modulus because some bulk moduluses are a function of temperature, and you can actually see that. And as the steel gets colder, it's going to get more brittle. And it's going to have less of that restorative property associated with it.
So it's pretty much like how much pressure it can take before it begins to, like its volume decreases pretty much.
It could be volume decrease, it can be a deformation. So if you think about a rubber band we usually do Young's modulus, right? Well, there's a region in the other rubber band where I can stretch it and it's going to go back to its original shape. There's another region in the rubber band that once I get past a certain point, it permanently deforms. And that's going to be related to its Young's modulus. Same thing happens with a bulk modulus. If I take a lead bullet, depending on the situation, I can bounce the lead up and down and it's not going to deform, it's going to act like a little steel ball. But if I put enough force to it, what happens? It deforms.
Okay.
Okay, it deforms. But what we end up with, because it's a material property, it's going to allow how the wave is going to transmit through it. It's like that slinky again. The slinky will compress and then it will expand back out and compress and it'll expand back out. And I'm looking at it almost on a molecular scale to have that happen. But we usually define it in terms of air, and so you can think about how the molecules are dealing with it, but you can also do the same thing in any solid material. So we get our element of our gas, and we can look at a cross-sectional area, and we can have forces that are equal to pressure times the area. And so we can start dealing with that, and we can look at it in terms of our change in time, and we can look at that increase, and we can get there, because what we're ultimately trying to get is that impulse of sound, just like we put the pulse in our rope. Remember we jerked at the rope and we put a pulse through it. We're going to do the same thing with sound, but it's related to the bulk modulus of whatever we've got, and we can look at it and we're going to actually start seeing that sound radiate as a sphere away. Because we're dealing in a volume now. We're dealing in a volume which is going to allow it to move. Okay, just. And so you get the speed, just like what we got the speed before. We got the speed in terms of the tension in the rope divided by the linear density. Now we get the speed is related to the bulk modulus divided by the overall density. So we get our mass per unit volume instead of mass per unit length, and we're dealing with that bulk modulus. And that's how fast the material is going to go through there. But I want you to look, remember, we got a change in momentum. And we talked about how all waves have energy. All waves are going to transport energy. And we're back to the speed, that square root of the elastic property divided by its inertial property. We're getting that same thing. So for a solid rod, where we're not dealing with the whole volume, it's going to be the Young's modulus. But when we're usually in air, we're dealing with the whole volume and how it's around the whole volume. We're going to be dealing with our medium. Now you're going to see this, and we're actually, no matter which side or how you're doing it, we are going to measure the speed of sound. We're going to measure the speed of sound over the course of the semester. That is what you have for the interactive this week, is measuring the speed of sound in a flame tube. That's where we're going to get, but we're going to also do it. But we also know, and this is one of those weird things, and if you think about it, we just talked about the fact that the bulk modulus is affected by temperature. The bulk modulus is affected by temperature. So if my bulk modulus is affected by temperature, and we know that the speed is related to the bulk modulus, we know that the speed of sound is going to have a temperature effect. And intuitively, this is the only correction we're going to make right now. But intuitively, you all know there are other things that affect the speed of sound. I want you to think and imagine.
A wall.
A wall. We're going to do a meditation today. All right.
Be the density of the medium,
Do what?
the density of the medium.
It's the density of the medium, that's going to affect the speed of sound. But when we talk about the speed of sound, we're usually talking about air or water.
Wind.
We know wind. Wind will affect whether or not we can hear something. And it's going to affect it two ways. Okay, it's going to affect it two ways.
Boosted.
One of the ways that it affects it is that wind in itself has its own noise, and so you're going to get lost in whatever noise it is that you're carrying. Okay? That's one thing. But the wind is also disrupting the medium in which the sound is going through. So if you think of it, you don't necessarily have this problem with water because the way things are going in water, but the wind, and we're going to actually see that a little bit there, but we're going to get the wind is going to help dissipate. It's going to act like a dampening force. It's going to act like a dampening force on our bouncy spring. So the wind's going to do that. So wind is one thing that does affect it, but that's not what I'm talking about. So let's think, like I said, we're going to meditate, we're going to imagine. Has everybody gone skiing?
Yes. Like snow skiing or what?
Snow skiing.
No.
No, okay, so let's ask the question. Has everybody been to a place where you've gone out and it's a crisp, cold morning with maybe a little bit of snow on the ground?
I'm not a morning person.
Well, it could be the afternoon as well. But what happens in that situation provided that the wind's not blowing? Because first of all, if the wind's blowing, we aren't out there anyway because it's freaking cold. But what does sound do on that crisp morning or that crisp time that you're out there?
Travels fast.
It's really clear, no distortion, it's going to travel fast. Now, let's do that morning that's about to come up on us because it is the month of September and the month of October. You go outside and it's wet and foggy.
Go slow, it's dampened.
It's going to be slower and it's dampened. You can't really hear, what happens to you on that crisp cold morning, you hear sounds that are way far away. I'm not going to lose it. You're going to hear that sound transport. On a foggy morning, if somebody is trying to talk to you maybe from 100 meters away, you may not be able to hear them at all. So, you do get, oh, that's interesting. My Wi-Fi kind of disconnected. So, for those of you who are online, if it doesn't come back pretty quick, the chat feature has just disappeared because it's my laptop. But you are still connected to class, so that's good. So we are really only going to be concerned for this semester about a temperature difference, but we know that we have other things that are also going to affect our speed of sound. And depending on how you look at it, you'll see the laboratory that we generally use, speed of sound is corrected a different way. We get a different correction. So the speed of sound at 0 is 331 meters per second. That's not the common one that we normally use. We normally use 343
It's not usually 0 degree.
because it's not usually 0 degrees and 20 degrees is more your average. So 343 meters per second is the speed of sound that we typically will use. But I'm also cautioning you about that because you better read the problem because depending on how the problem's worded, you may have to correct for the speed of sound in terms of the temperature.
So at what temperature does the speed of sound travel the fastest?
Oh.
The highest temperature.
I don't do that calculation.
Wouldn't that depend on the humidity though? Would humidity-
Well, it will,
That's a whole
but,
other factor.
but, you know, we're, like I said, we're just gonna focus on temperature.
Okay. Thinking too hard.
Is that the reason why, like, if there was no wind on the earth, you still wouldn't be able to, like, chat with someone a state away from you, you know?
Well,
If you were just in an open field, like, really long, and there was no wind, would it travel that far?
yeah,
So theoretically, if all the wind and
the
the
problem
wind stopped.
though is intensity, and we're about to get to that.
You just have to be really low.
You just need a.
No, the problem is intensity. So let's go back and let's think for a second. Here on the surface of the Earth, the acceleration due to gravity is 9.8 meters per second squared. Actually, here in Tonkawa, it's 9.78. We've measured it enough times. We know it's not quite 9.8. Over in Enid, it's pretty close to the same. But we know if we leave the Earth, because we all did that problem, right? If we leave the surface of the Earth and we travel up 2 miles above the surface of the Earth, what happens to the acceleration due to gravity? That 9.8.
It drops.
It falls off, right? It's going to be something lower. And if I get further and further away, what happens? So if I go back and I look at that force is proportional. If we look at Newton's fundamental law of gravitation, force is proportional to 1 over r squared. Okay? Force is proportional to 1 over r squared. We're going to see the same thing happen pretty quick when we do Coulomb's law. And you guys know Coulomb's law from chemistry. Coulomb's law is K is equal to Q1, Q2, charge on the first object, charge on the second object divided by r squared. It also is proportional to 1 over r squared. So if I take my two charges and I bring them close together, the force between the two is going to be stronger than if I have them way, way apart. It's going to drop off as 1 over r squared. Well, what happens to us, and we know this, because if I'm standing right next to the subwoofer at a concert, it's painful. But if I go to the other side of the stadium, I'm certainly not going to feel the thump, thump, thump. I might hear a muffled thump, thump, thump. So the intensity, two things are happening to us with sound, because sound is going to radiate out as a sphere. I'm going to drop off intensity as I get further and further away. I'm going to drop off intensity. So even though the sound is still going to travel, because sound travels out like this, it travels out radially, I am going to lose some of that in terms of the distance, but I'm going to have it. Now, we've all been to the Science Museum, right?
Yes.
And there's this big parabola dish thing, and they tell you to stand on the little X, right? They tell you to stand on the little X. And you got your buddy on the other one. There's another parabola dish on the other side of the room, and you got your buddy standing on the other desk, and you can whisper, and your buddy can hear it. But nobody else in the place can. Because we talked about that waves can be reflected. And that, just like I do with mirrors and light, sound's going to do the exact same thing. There's a place that the focus is going to occur. And you can have a lot of freaking fun on the AM radio dial. I love the AM radio dial, because the AM radio dial at twilight, you can pick up radio stations. I can easily pick up a Los Angeles radio station without too much trouble. KTLA, I think, is the radio station I can pick up without too much trouble. I can almost always pick up the Salt Lake City radio station without too much trouble. I actually got one the other day. I was playing with it. This was probably March of last year, playing with it on the way home after my evening class. I think I got one out of Toronto.
How do you do that? You just like scroll through?
Yeah, scroll through and you start listening and you try to listen to the call letters. It's on the AM radio dial. The FM radio dial, it doesn't work so much, and it's how sound bounces off and bounces through how the radio waves, they're very much like sound waves. It's how they bounce through the atmosphere and get reflected, and you can pick up, twilight's the best time to play with it.
Why is that?
It's just where the curvature of the earth is, and you can start playing with it a little bit more. But yeah, twilight seems to be the best time, so you can have some fun.
So why does, whenever you have two cans,
Mhm.
like some string in between them, how
Mhm.
does that work?
It's the same thing. You're sending the vibration through the string, making sure the string is taut, and then you're using the resonator, the can as a resonator on the other end. Okay, so the whole idea behind all of this is that we get that the speed of sound is going to be related back to the pressure, but that gets us to the fact that this gets us to intensity. All right, this gets us to intensity. And so here are some speeds of sound in various media. You can see as I drop off gases or change gases, I'm going to get a change. We use 343. You get your variety of different things. The speed of sound is going to be related to that bulk modulus. We know it's going to get area, or we know it's going to carry energy. We want to have that, and we can go back and we can go in and we get to power. Power is going to be related to the force times its velocity. Power average is going to be related to that whole mess of the mass. And I think you guys have some homework problems that did this. I don't usually ask about power because that's not what I want to focus on and when it comes to tests and things like that. My focus of all of this comes down to a couple of things. One, waves travel and have energy. And I want you to be able to deal with that energy part of it. I want you to realize that when we get to this, waves have a wave number, and we get to that aspect of it. I want you to be able to take information and create that wave equation, or that simple harmonic oscillator equation, and I want you to be able to pull information out of it. This stuff is just fun to know about, and depending on your area of engineering or your area of science that you're going to, this stuff becomes more important. Because if I want to run an ultrasound, I need to know about this because we don't want the ultrasound to damage, if I'm doing it for imaging, we don't necessarily want it to damage what we're trying to image. If I'm doing something that's ultrasonic, like to blast a kidney stone, I need to know what kind of power that I'm putting in there. If I'm doing this to get a parts washer, I take apart the plant that I went to yesterday. It was pretty cool. I got to see all kinds of the internals of turbines. So it was really cool. And so what they do before they start working on repairing the blades on those turbines, they put it into a parts washer and they use ultrasonic to clean it. Jewelry uses a lot of jewelry uses ultrasonic cleaners. But I got to know those power pieces for it. So I've got to introduce the topic. I am not necessarily focused on it. You're going to have a couple of homework problems associated with it, but that's not where my big focus is. But that does get us to intensity. And intensity is related to my average power divided by the area. And when it comes to sound, intensity is really, really important. So, I've had some fun following COVID news. Oh, I'm about to lose everybody, but we'll get there. So I'll tell my story here. So, Nancy Pelosi gets out there and she says, okay, it took us 8 weeks to reach X number of COVID cases. Yeah, all right. And then in 4 weeks it took us, and she gave a number that was really close to 2X. And then in 2 more weeks, we hit 3x. Okay? We know that that's a mathematical function. It's called an exponential function. We get that. When we talk about intensity for sound, we're actually going to use a logarithmic function. And we will get to that on Monday, apparently, since I am at 119.